It's a great pleasure to introduce Isabelle Grenier from Paris, and she's going to talk about Planck, Fermi, and the dark gas.
Thank you, and sorry, because you're going to have to move back from z equal 2 million down to 0, so it's quite a drop. And you will also have to go from the most abundant form of photons in the universe to the rarest species, which are gamma rays. So sorry for the double drop there. So you're all familiar with the Planck sky, the microwave sky, with all those ingredients, emission ingredients from synchrotron free dust and CMB, but you may not as aware perhaps of the ingredients of the gamma ray sky, so let me review a little bit for you. Here you have the all sky map, the Fourier sky map that we've accumulated with Fermi, actually above a GeV and not 30 GeV, it's 0.30. 0.030, it's 30 MeV to 300 GeV that we're looking at, and here you're looking above a GeV to get a decent angular resolution. And what you see primarily is the Milky Way, because you have all those cosmic ray interactions with the gas. And second, you see a lot of point sources. And the cosmic ray flavors, you have mostly nuclei hadronic interactions in those maps, and a little bit of electron activity, which is they are upscattering whatever photons and CMB they find on their way. And so they are upscattering and makes a diffuse glow around that is hard to see on those maps, which would look pretty much like this in the sky. And then you have funny types of cosmic ray, not the regular cosmic rays that are coming from those Fermi bubbles. This is loop 1, but here you see the Fermi bubbles, which are either cosmic rays escaping from the central regions or some activity from the central black hole. So I will concentrate today mostly on the diffuse interstellar emission because there are a lot of synergies between Fermi and Planck, and we can work together to study the haze and the bubble that has been done and will go on a lot more. Here you see the Fermi lat sky map above 10 GeV, so you can see the bubble sticking out much better. And there is also a lot of activity, future activity, not started yet, probably on the interstellar radiation field, the infrared part of it, which gives us that glow of inverse Compton emission into the gamma ray range. We've heard yesterday a lot about point sources on blazars, how crazy the sky is for AGN when you compare what happens in the radio to millimeter wave bands to the gamma rays. Same thing about spectral energy distribution in supernova remnants, but what is really most of our joint force here is to work on the gas, so I will concentrate on the gas more. And to tell you a little bit about cosmic ray physics and what we find with Fermi at the moment, before using the cosmic rays as tracers of the gas, let me just remind you that there are two things that we can work together on very, very importantly for you, which is here you see the electron spectrum that are raining down directly on Fermi and we're detecting in the calorimeter. And this is the spectrum we measure for the electrons. First is changed between before and after Fermi. And here you see the energy band that corresponds to the synchrotron emission that you see with Planck and you've seen with WMAP 2. And so this is important to understand. Here, this is the local measurement inside the solar system. This is the remote measurement through the radio maps into the interstellar medium. So if you connect both, you have a hand on the magnetic field in the Milky Way. And so you can do that for the regular and the random component, modeling that. And there are people in the room like Andy Strong and Elena who are doing that for you. And so what you have here, you can do it first with the total emission, but you can also do it with a polarized emission. So you could have a good constraint on the global magnetic field and global distribution of the field in the Milky Way. And also, you have to connect the radio surveys and the microwave surveys to what you find locally in terms of cosmic ray electrons. And what you find is, if you model them globally, you have to have not a single Paolo, as many people are assuming, but you have a break, several breaks in the electron spectrum. One is around a few GeV. Another one is seen here is hardening above tens of GeV. And so this affects how you model the synchrotron between the radio surveys and WMAP or Planck. So this is important for you. And you see that the primary electrons are dominant, but there's a significant fraction of secondary electrons that come from the hadronic interactions of the cosmic ray nuclei with gas. So you should not forget about those. And we have a constraint on those from the gamma ray maps. From the other component, the pion component. Oops, sorry, this is the one. Okay, so in terms of nuclei, and everything I'm going to say now will concentrate on cosmic ray nuclei. For the rest, is when you look, it's surprisingly simple and nice, well behaved. When you look at the sky off the plane or in individual clouds, you see here in the H1, I'm pointing out molecular clouds, but there's H1 around them. And so when you see the contribution of the cosmic rays, the gamma ray emission by the cosmic rays in the H1, you see that spectrum is remarkably uniform from one spot to the next. There are less than 20% variations that we measure. And what you find here is exactly what we understand from the cosmic rays we measure within the solar system at Earth. So this is really nice to understand a little better about how cosmic rays penetrate into the solar system and about solar modulation. So what is another point which is for you to take away, because it's very important in terms of tracing gas mass, is the fact that here, if you look at the emissivity that comes from other phases than the H1, here you see the gamma ray emissivity as a function of in the CO phase versus the H1, or in the dark phase versus the H1, you see linear scaling everywhere, which means that the cosmic ray spectrum we derive in those phases is pretty much the same as the one we have in the atomic phase. So that means that the cosmic rays nuclei are really penetrating rather uniformly, at least at the level of precision we have here, down to parsec scales, even in the dense molecular phase. And from a few per cc or less than per cc all the way to 10 to the third or fourth per cc in gas, cosmic rays don't care, they just go through. Okay, and what is a little more surprising to us is we've done that in local clouds, but we've also done that further away. Here you have the sun and spiral arms, and we've done that in big complexes in the local arm and Perseus arm and so on in Cygnus region. And we find surprisingly the same spectrum, which is consistent with what we have at Earth. And very little variations of, less than a factor of 50% or something equivalent, which means that the cosmic rays are very loosely coupled to star formation rate, source distribution, whatever. And so it gives a severe headache to the people who try to propagate cosmic rays from their sources, supernova remnant sources. But in terms of tracing the interstellar gas, it's a beauty, because it means they smoothly permeate whatever gas they are running into, and so you can use them nicely to trace the gas. And that applies to small clouds of a few thousand solar masses all the way to big complexes of a few million solar masses. So this is really important. And so that's how Fermi and Planck can join forces, because you see the dust and we see the cosmic rays flooding the gas, and we can really do something jointly in order to understand better how the mass tracers are working. And if you have, constant gas-to-dust ratio or conversion between H1 and CO. So here you see the gamma ray map on top, where we've removed anything that is not interstellar in origin. And here you see the optical depth map that was presented to you by Marc-Antoine 2 days ago. as you can see, there's a striking resemblance between the two maps. The two maps, I've offset them to the somewhere around 270 in longitude, so you can see both the center, the striking features in the galactic center and towards the galactic anti-center, because that's where they are more conspicuous. And there is really a very strong correlation between those two maps, which means that the dust and the cosmic rays are acting as full gas tracers, both. And but in the plane, it's always difficult because you have to, disentangle, because there are integral tracers. They trace everything along the line of sight. You have no distance or velocity measurement, as you do in the radio, because you have velocity and kinematic information about where the gas is located. So we have to do integrals along the line of sight. In the plane, it's a nightmare. But off the plane, that's where we're starting to work, is much easier because you have fewer components. And the components you have are typically the atomic gas you see in H1, the dense molecular gas you see in CO, the dark neutral gas, which is in between those two, which I'm coming back to, and what you learn from the correlation with either dust or gamma rays with H1 is how much dust you have per H unit, and here how many cosmic rays you have per H unit. Then from the correlation with the CO, what you get, if provided you have the same cosmic ray rate flux permeating H1 and the dense phase, then you extract the conversion factor CO2 H2. And you can do the same thing if you assume that the gas-to-dust ratio is the same in the H1 and CO phases, and the dust emissivity is the same in those environments. You can then extract the conversion factor between the CO and H1 correlations. And then you have the leftover. And the leftover, thanks to Gary Hinshaw, who doesn't know he initiated the whole thing, but I can tell him the story. There's the leftover information. That leftover information is really an important part of the phase of the interstellar medium, as I'm going to show you in a second. And then you add, on top of all those modeling, you add whatever is non-interstellar in order to match the data. So what we were doing back 2 years ago with the early Planck, and what was published at that time was you had the optical depth map from the dust, and you removed everything you knew about H1 and CO, and you were left with this gray stuff or green stuff. All the colors are fading away on that screen. And what we had in the gamma rays was exactly the same. And but as you can see, fewer photons, definitely. And so Poisson noise a lot all over the place. And what we can start to do now with much more accurate data is go back to those maps which we're just starting to analyze, and as a teaser for all the studies that are going to come, I'll concentrate on this cloud, which is called the chameleon. As you can see, there's a good correlation between the two, and I'll peel them off a little bit. So here is the zoom. On the left you have the optical depth map from Planck. On the right you have the lat Fermi data, which instantly I will remove anything that is not interstellar, which is inverse Compton emission, point sources, etc. So you have here a very, very nice correlation between the two. You don't need to plot them against the other, because you instantly see that they are tracing the same structure, spatial structure, all over the place. So what you can analyze is model that as a function of H1, CO, and everything you like, and you peel off whatever you understand from the correlation with H1 and CO. On the left, that's what's left from the dust. On the right, that's what's left from the gamma rays. And they see the same thing. And as they see the same thing, there is no way that the cosmic rays know about the dust, nor about the radiation field of the dust. It would provide you with too few gamma rays to create the map on the right. And vice versa, there is no way that the cosmic rays would make the dust shine more or less. So what they are tracing is the fact that this map resembles very much this one, tells you that there is much more mass of gas that both are picking up because dust is mixed up in the gas and because cosmic rays are just flooding through the gas. And what is nice too is if you divide this one by this one, then you get the dust opacity in that phase, and you find a gas to dust ratio, which is quite normal. So what is nice and important too is the fact that here you have the H1 map, the local H1 map, plus some intermediate velocity cloud that happens to be in the same field, and here you get the mass that you derive from the gamma rays and turn the CO into mass, and here you turn the dark gas from the dust thanks to the gamma rays into column densities. They are all the same scale. As you can see, the dark gas component is a major constituent of that map. It's not negligible. It holds a third of the mass compared to the H1, but 3 times more mass than the revealed CO phase, dense phase. So it is not a negligible partner in the interstellar medium, and it's the only way we have to trace it, is compare the gamma rays with the dust. And so what's the recipe for that gas? It's probably a mix of dense H1 and a mix of diffuse H2 with very little CO, because we looked again last night into the Planck data, and the CO we've removed from the correlation here is everything we could find, and Planck did not see more than we had here. So if there is CO, it has to be extremely faint. And also, the gamma rays tell us that probably we measure the mass, the true mass of the H1, and we cannot hide much mass in terms of absorbed H1. So what's the recipe? I have no idea. But another piece of information that the comparison is giving you is the fact that even though there's a beautiful correlation here, if you look carefully, it's not a perfect correlation. So there's a lot to be learned in between. And so if you divide one by the other, and you just do that above a certain threshold to avoid biasing or constants and things, what you end up here is that rate, whoops, this has disappeared, it was the scaling. Here you see the ratio of the two, and instantly you can pick up the chameleon, Taurus, Orion, Ophiuchus, and it tells you that that ratio evolves with the total gas you're expecting from the nearby clouds. And you see it better on this plot here, where you have the ratio of the dust optical depth to the gamma ray flux, which you can use as a total gas tracer, and then just look at the dust opacity, or emissivity if you prefer. And what you find is that it varies as a function of the total amount of gas that you have. And it varies smoothly but steadily when you go from diffuse H1 to dense H1. And that's pretty much what Marc-Antoine was showing you 2 days ago, which was you have very low tau over NH in the diffuse H1, and then you go into the denser H1, it was rising. And if you move to even denser medium, which is traced by CO, and you add what the CO looks like, then you have a steady increase. What you have here on the gamma ray side is you get the dark gas in addition to H1 and CO, and you find the same increase. And what Peter Martin was telling us is he has hints of dust emissivity evolution. That, in other words, the dust in the dense medium seems to be more emissive than the dust in the very diffuse H1. And the trend he was telling us is that trend. So the gamma ray is somewhere, I scaled it manually here, but the trend is there, and it seems that we're looking at the same thing, that the dust evolves. It's not emitting the same way as it goes to denser and denser medium. So that stresses points, tensions is the fashionable word nowadays. So that stresses tensions that we had before, which here you have the CO to H2 conversion factor, because if you look at this curve, you see that there's a rise in the H1, but there's also a steeper rise when you get into the molecular clouds, the dense molecular clouds. And so what it tells you is that if you derive the X ratio, the CO2H2 conversion factor with the dust or with the gamma rays or other means, you have a discrepancy. And that discrepancy was visible here. This is galactocentric radius and the evolution of XCO in the Milky Way. Here are local clouds that we've measured in gamma rays. Here's the local clouds that were measured with Planck. And there was a factor of 2 discrepancy. And people brushed it up because they said, okay, different data, different binning, different H1, different CO, and so on. Here we're, in the chameleon, we're working with exactly the same thing, the same method, the same data, the same bins. We find that discrepancy of a factor of 2 again, so we can't just hide it under the carpet. And the second aspect, which is another tension, is the fact here you see the X ratio measured by the gamma rays in well-resolved clouds. Here you see the X ratio measured by the gamma rays again, same technique, in farther away complexes. And we find another factor of 2 here, which tells you that there is something, if you look at a big complex from far away, you don't measure the same amount of molecular gas associated with CO than you do when you have parsec scale resolutions inside the clouds. So there's something here to understand about how we integrate or how we assume what is associated with the CO. So there are, and also as I mentioned, from the diffuse H1 all the way to dense molecular clouds, there could be dust emissivity up to a factor of 4, so it's not negligible. And so we have to test that on many other clouds, which we're going to do right now, and we have to understand the physics behind that tell us that there are such variations, because they are the only tracers you can use further out in external galaxies or anywhere. So we have to measure and calibrate those tracers locally with as much as we can, and it seems that the cosmic rays can help us a little bit in that game. So this was done thanks to many people, and so I have the privilege of showing you 2 sets of logos instead of 1. So there's an X ratio variation between the dust number of logos and the gamma ray number of logos, but thanks to many, many people, this is possible, and there's a lot more to come in the next months. Thank you.
Okay, thanks very much. Questions? Jean-Loup?
On your plots of the opacity versus column density, where you see this change with denser and denser gas, or at least higher column densities, below 1 to the 10 to 20, there is a rise again. That's probably due to the CIB, which is not separated from that. Is that right?
According to Marc-Antoine and François Boulanger, I think it is rather linked to the WIM, to the hot gas, rather than CIB. But the gamma rays won't help you there, because it's much too faint for us. Okay? So here we cut. This number we cut here. No, there are no numbers. We can't see that rise, because it's much too faint gas for us to separate from all the other inverse Compton emission, large-scale stuff.
Further questions? Okay, one there.
So not really a question. You come up with this dark gas. Let me mention that there is a theory called gravitational hydrodynamics that puts forward that would be a lot of dark baryons in the galaxy, even up to the point that they could make up the whole dark matter. I will take this up with you later.
I think we'll just stick to a few times what we see in the H1 and CO, which is, maybe I think in the inner galaxy we're going to confirm those numbers, but we could add maybe twice as much gas as we've seen before, but nothing to do with the dark matter or dark baryons. It's just, we're trying to understand how the tracers behave, because they are obviously, now we've reached the level where the interstellar matter tracers behave non-linearly, which we've always known, but now we've reached the level where we can show and try to understand how non-linear they are. It's not just, linear coefficients is easy to handle, but it's not the truth. But we're far from having the whole of dark matter made of this gas, at least in the inner galaxy.
Okay, one more question. There's one at the back there.
The XCO calibration seems great, seems the best way to do it. But do you have to worry about magnetic shielding in the densest part of the clouds where your factor goes up?
Sorry?
Do you have to worry about magnetic shielding of the cosmic rays?
Well, that factor of 2 between the cosmic rays and the dust, we've been discussing it heavily. I tend to think that I would trust the cosmic rays better and think that the dust evolves in its emissivity. We're going to test that very seriously, as you can guess, because it's funny to understand. First, GeV and tens of GeV cosmic rays, the magnetic field is there because otherwise you wouldn't get the synchrotron emission. It's very difficult to prevent them from just streaming along the fields and getting into the clouds. And also because we find no spectral evolution between the dense phase and the very diffuse phase. So it's very difficult to think that half of the cosmic rays would remain outside with no spectral signature at all. This is weird. So we're going to pin down those error bars and make them as small as possible so we can really test that. But if we can somehow, think that the cosmic rays are safer in terms of looking at the total gas, then we have to understand why the dust could evolve as much as a factor of 3 or 4 between the different phases.
Okay, well, it's time for coffee now, and we should come back at 11:15. But let's thank all our speakers of this first session again.
Do we have to turn off something?
I think please. Yeah.
Okay.